The electric battery, the electric motor, and the electric generator represent three pivotal inventions in electrical history. These innovations have profoundly shaped our world, enabling advancements across numerous fields. Alessandro Volta's invention of the electric battery in 1800 marked the dawn of a practical source of electricity. Before Volta's battery, scientists relied on static electricity or cumbersome devices like lead and draws to produce electrical charges. These methods were impractical for sustained experiments or powering devices. The voltaic pile, as Volta's battery was known, consisted of alternating discs of zinc and copper separated by cloth soaked in brine. This simple arrangement produced a steady flow of electricity, a continuous current that could be used to power devices and conduct experiments. The impact of the electric battery was immediate and far-reaching. It provided scientists with a reliable tool for studying electricity and magnetism. It enabled the development of technologies that would transform communication and industry. The telegraph, for example, relied on a steady source of electricity to transmit signals over long distances. Without the electric battery, the telegraph would have been impossible. The telephone, another revolutionary communication device, also depended on the electric battery to power its operation. The electric battery also paved the way for advancements in medicine and other fields. It enabled the development of electrotherapy, a technique that uses electrical stimulation to treat various medical conditions. It also made possible the development of portable electrical devices, such as flashlights and radios. Michael Faraday's invention of the electric motor in 1821 marked a significant leap forward in the application of electricity. The electric motor converts electrical energy into mechanical energy, providing a clean and efficient way to power machines. Before Faraday's motor, machines were primarily powered by steam engines or internal combustion engines. These engines were often bulky, inefficient, and polluting. Faraday's first electric motor was a simple device that used the interaction between a magnetic field and an electric current to produce motion. A wire carrying an electric current was placed in a magnetic field, causing it to rotate. This simple principle formed the basis for all electric motors that followed. The impact of the electric motor was transformative, revolutionizing industry and transportation. Electric motors powered factories, enabling mass production and increased efficiency. They replaced steam engines in trains and ships, making transportation faster and more reliable. Electric cars, buses, and trams emerged as cleaner and more sustainable alternatives to gasoline-powered vehicles. The electric motor also found applications in countless household appliances, from washing machines and refrigerators to vacuum cleaners and power tools. Its versatility and efficiency made it an indispensable component of modern life. Michael Faraday's invention of the electric generator in 1831 completed the cycle, providing a means to convert mechanical energy back into electrical energy. The electric generator, also known as a dynamo, made possible the large-scale generation of electricity in power plants. Before Faraday's generator, electricity was primarily produced by batteries, which were expensive and inefficient for large-scale power generation. Faraday's generator used the principle of electromagnetic induction to produce electricity. When a conductor, such as a wire, is moved through a magnetic field, an electric current is induced in the wire. This principle is used in generators to convert the mechanical energy of a rotating turbine into electrical energy. The impact of the electric generator was revolutionary, enabling the widespread use of electricity. Power plants could now generate large amounts of electricity to power homes, businesses, and industries. Electric lighting replaced gas lamps, improving safety and convenience. Electric power enabled the development of new industries, such as aluminum production and electric steel making. The electric generator also made possible the development of the electric grid, a network of power lines that distribute electricity over long distances. The electric grid allows electricity to be generated in centralized power plants and delivered to consumers wherever they are needed. These three inventions, the electric battery, the electric motor, and the electric generator, are interconnected and mutually reinforcing. The battery provides a source of electricity to power the motor. The motor converts electrical energy into mechanical energy to drive machines and devices. The generator converts mechanical energy into electrical energy to power our homes, businesses, and industries. Together, these inventions have transformed our world, enabling advancements in communication, transportation, industry, and countless other fields. They have laid the foundation for the modern electrical age and continue to shape our lives in profound ways. Understanding the fundamental principles behind these inventions provides valuable insights into the workings of our technological world. Consider the electric battery. Its operation relies on electrochemical reactions that convert chemical energy into electrical energy. The battery consists of two electrodes, typically made of different metals, immersed in an electrolyte solution. When the electrodes are connected by an external circuit, a chemical reaction occurs that releases electrons. These electrons flow through the circuit, creating an electric current. Different types of batteries use different chemical reactions to produce electricity. Lead-acid batteries, commonly used in cars, use a reaction between lead dioxide and sulfuric acid. Lithium-ion batteries, widely used in portable electronics, use a reaction between lithium ions and a metal oxide. The voltage of a battery depends on the chemical reaction that it uses. A typical lead-acid battery produces a voltage of approximately 2 volts per cell, while a lithium-ion battery produces a voltage of approximately 3.7 volts per cell. The capacity of a battery is a measure of how much electrical energy it can store. It is typically measured in amp-hours, which represents the amount of current that the battery can deliver for a specified period of time. Consider the electric motor. Its operation relies on the interaction between magnetic fields and electric currents. The motor consists of a stator, which is a stationary part that produces a magnetic field, and a rotor, which is a rotating part that carries an electric current. When the current flows through the rotor, it creates its own magnetic field. This magnetic field interacts with the magnetic field of the stator, causing the rotor to rotate. Different types of electric motors use different arrangements of stators and rotors. Direct current, or DC, motors use a commutator to switch the direction of the current in the rotor, allowing it to rotate continuously. Alternating current, or AC, motors use alternating current to produce a rotating magnetic field in the stator, which drives the rotor. The speed of an electric motor depends on the frequency of the alternating current or the voltage applied to the DC motor. The torque of an electric motor depends on the strength of the magnetic fields and the current flowing through the rotor. Consider the electric generator. Its operation relies on the principle of electromagnetic induction. The generator consists of a stator, which is a stationary part that produces a magnetic field, and a rotor, which is a rotating part that carries a conductor, such as a wire. When the rotor rotates, the conductor moves through the magnetic field, inducing an electric current in the conductor. This current is then collected and transmitted to an external circuit. Different types of electric generators use different arrangements of stators and rotors. Synchronous generators use a rotating magnetic field to induce current in the stator windings. Induction generators use a rotating magnetic field to induce current in the rotor windings, which then induces current in the stator windings. The voltage of an electric generator depends on the strength of the magnetic field, the speed of rotation, and the number of turns in the conductor. The frequency of the alternating current produced by a generator depends on the speed of rotation and the number of poles in the generator. The electric battery, the electric motor, and the electric generator are fundamental components of countless devices and systems that we rely on every day. Understanding their principles of operation is essential for anyone interested in electricity and technology. The ongoing development of these technologies continues to drive innovation and improve our lives. For example, advances in battery technology are leading to longer-lasting and more efficient batteries for electric vehicles and portable electronics. Advances in motor technology are leading to more efficient and powerful motors for industrial applications and electric vehicles. Advances in generator technology are leading to more efficient and reliable power plants that can generate electricity from renewable sources such as wind and solar energy. The electric battery, motor, and generator are not just historical artifacts, they are dynamic technologies that are constantly evolving to meet the changing needs of our world. Their impact will continue to be felt for generations to come. We can look at the applications of each of these in more detail. Firstly, consider the electric battery. Beyond powering small electronics, batteries are essential for backup power systems in hospitals and data centers, ensuring critical operations continue during power outages. They are also crucial for energy storage in renewable energy systems, allowing solar and wind power to be used even when the sun isn't shining or the wind isn't blowing. The development of solid-state batteries promises even greater energy density and safety, potentially revolutionizing electric vehicles and grid storage. Secondly, the electric motor's impact extends far beyond industrial applications. Electric motors are essential for medical devices such as MRI machines and ventilators. They are also increasingly used in robotics and automation, enabling precise and efficient movements in manufacturing and other industries. The development of more efficient and compact electric motors is crucial for reducing energy consumption and improving the performance of electric vehicles and other applications. Thirdly, the electric generator plays a vital role in ensuring a reliable power supply. Modern power plants use generators to convert energy from various sources, including fossil fuels, nuclear power, and renewable resources. The development of more efficient and sustainable generators is essential for reducing greenhouse gas emissions and mitigating climate change. Advances in generator technology are also enabling the development of microgrids, which can provide localized power generation and improve resilience during grid outages. These three inventions work together to create a complex and interconnected electrical system that powers our modern world. The battery stores energy, the motor converts electrical energy into mechanical energy, and the generator converts mechanical energy into electrical energy. Understanding how these technologies work is essential for understanding the challenges and opportunities facing our energy system. As we transition to a more sustainable energy future, these inventions will continue to play a critical role in powering our homes, businesses, and transportation systems. They will also enable the development of new technologies and applications that we cannot even imagine today. The future of electricity is bright, and these three inventions will continue to be at the forefront of innovation.